Hello, Professor Fefferman.
Oh, please, Charlie.
So you're famous because every time you get into one of those new fields of mathematics that you enter, you change the DNA of the space. I want to talk about one particular thing you did, which is you got involved with computer-assisted proofs as you were already revolutionizing another field, which was mathematical physics and your proof of stability of matter. So you managed, that was like a dual change of two fields almost at the same time. Tell us about the context of that.
Well, I would say there are two aspects. There is the computer and there is stability of matter. So regarding the computer, in the early 1980s, we brought an Apple II Plus into our home. We were concerned that our little children would become addicted. In fact, I became addicted. But the feeling ultimately was that one day the computer would be so important it would be like the telephone. Little did we know that the two would merge into one object. If I remember correctly, my name for our Apple II Plus in our house was the toy. Okay. I remember producing various simple mathematical constructions using it, and I had in mind that it would be fun to bring it to bear on anything. All right, from the mathematical side, I became interested in stability of matter through quantum statistical mechanics. So simply, why are there the states of matter that we see in the world? Why, the simplest of which, let's say, is a gas. So why is there hydrogen gas? And I found a proof of this, provided that a certain constant in an inequality, the inequality was stability of matter, was sufficiently small. It was known to be finite. It was known not to be very big, but it was not known to be quite small enough for my proof to apply. Of the formation of atoms and molecules. So I got involved for a long time in trying to produce best constants in inequalities. In one of these inequalities was a variant of stability of matter called relativistic stability of matter. In that, the usual kinetic energy from quantum mechanics is replaced by something smaller. And that has the consequence that if the system is too big, it will simply collapse. And the question then becomes, well, exactly how big does the system have to be before it collapses? I was able to reduce this to some question about particular ODEs depending on parameters. Ah, wonderful, I can solve ODEs using the toy. And I did so. And the desired conditions held. I thought that was lots of fun. I lectured on it. I gave a graduate course on it. And one of the participants, Rafael de la Llave, came up to me afterwards and said, I can supply a rigorous proof of those those computations. He explained to me about interval arithmetic. A computer, of course, cannot represent an exact real number. An exact real number has infinitely many digits, and a computer has only finitely many states. Things are even worse if you try to represent a function on a computer. So what can you do? Well, you can produce, let's say, a very small interval. And that interval can be the computer's way of telling the user that the desired number is somewhere in there. If you want to add together two numbers, well, each one is in its own little interval, the endpoints of which are exactly represented in the machine, and then the computer should then produce, as a result, an interval which is guaranteed to contain the sum of any two numbers in their respective two intervals, and similarly for products, and similarly for quotients, except oops, if the interval you start with contains 0, then you're out of luck and you should simply abort your program. Given any particular computation with exact real numbers, you can at least try to make it rigorous by imposing intervals over it. I became a consumer of interval arithmetic. I feel a little embarrassed saying this because my interviewer has been a producer of interval arithmetic. Okay, that was a success. We produced a rigorous proof of the desired conditions. They involved something that was new at the time in the interval arithmetic business, namely fat intervals. If you want to show that for a range of parameters something never happens, you could represent part of the parameter range as a fat interval and hope that even though the original idea of interval arithmetic was to keep the intervals as thin as possible, nevertheless, this works with fat intervals. So that was my first encounter with interval arithmetic. Since then, I became interested in large individual atoms. Chemistry happens because of small imbalances in the ground state energies of atoms and molecules. There are famous heuristic derivations in physics going back to, oh my God, maybe the 1920s or early 30s, as to the asymptotics of the energy of a large atom. And so originally, I thought that it might take about 6 weeks to make that rigorous. In fact, it took a few years and 1,000 pages. Ultimately, it all came down to proving some properties of solutions of a particular ODE. And again, I'm speaking to the producer. I was the consumer of that part of the effort. And interval arithmetic came to the rescue and proved that the desired properties of the ODEs held. Some Hamiltonian flow was not periodic, and this confirmed, I think, what is still the most accurate known asymptotic expansion of the energy of a large non-relativistic atom. Of course, atoms in real life are not as big as all that, and so there's the interesting question of finding correct upper and lower bounds for the ground state energy of atoms of atomic number, let's say between 1 and 92. Again, I think I'm talking to an expert, and interval arithmetic played a great role in that. So that was my, I would say, the first of my interactions with the computer world.
It's fantastic. It's a great story. Now, your toy, yes. You already said, you already thought it would be as important as the telephone, and as you mentioned, they eventually merged. What other things did you imagine that then either happened or didn't happen?
I got involved as part of a consulting gig. I got involved with neural networks, and I heard of a problem, the uniqueness problem for neural networks. If two neural networks do exactly the same thing, are they in fact exactly the same neural network? There are obvious symmetries. And I thought this was an interesting problem, even though, of course, in reality, neural networks are successful because there are many, many, many different ways to do more or less the right thing. So the question of whether two neural networks do exactly the same thing is fun to think about, but maybe not the reason why neural networks are so important. In any event, I had absolutely no idea how to attack the problem, but something very fortunate happened. Namely, I heard a rumor that it had been solved. And so I thought, oh, well, maybe it's not as hard as all that. And so, well, what could be the solution? It couldn't be too complicated. And I thought, aha, maybe the thing to do is to think of neural networks acting not just on real inputs, but on complex inputs, and to think of what neural networks do in terms of complex variables. What are the relevant analytic functions and what are their singularities? And under generic conditions, you can simply read off everything about a neural network by just looking at the singularities of its analytic continuation. First of all, analytic functions often don't have unique largest domains to which they continue analytically. Think of the square root of z. You can make lots of different slits, but for neural networks, I should say, based on the hyperbolic tangent activation function, for such neural networks, which at least at the time were standard. Now I think maybe they are less so, but for such, there is a unique largest domain to which the output continues. And what happens, let's say in the simplest case in which there's one input and one output, the general case can easily be reduced to that. There are, in the complex plane, there are arithmetic progressions. And those arithmetic progressions encode the positions of the very first layer beyond the input. And then if you look at each point or a typical point of one of those arithmetic progressions, it is the limit of another sequence of points, which after linear fractional transformation again becomes an arithmetic progression, and those encode the second layer. But each point of those is in turn an accumulation point of another sequence, the limit point of another sequence, and that encodes the third layer and so on. And you can simply read off the whole structure of the neural net. So that, I mean, it was very lucky that I heard the rumor that the problem had been solved. In fact, it had not, but that analytic continuation was the key. And that provided uniqueness for generic assumptions about the weights and thresholds of the neural net. But I thought it would, in fact, be much, much more complicated to understand the full problem, not under generic assumptions, but absolutely the full problem. All right, decades passed, and recently, I think maybe in the last, I don't remember, maybe a year ago, 2 years ago, not so long ago, I got an email from a young doctoral student at ETH, Werner, who wanted to talk to me about his thesis about neural networks. Oh, sure. Okay, let's talk. I don't remember whether we met in person or we Zoomed, but it turns out that he had a complete solution of the problem. He did not assume that the networks were arranged in layers, which was the default assumption when I worked on the problem. They could have any architecture at all. He spelled out precisely the conditions under which the theorem applied. There were ridiculous things. For example, you can insert a node into a neural network which does not output to anything. And of course, it then doesn't matter what inputs to that node, and that would be an obvious counterexample to uniqueness. And so there is a short list of completely obvious conditions that you want to impose in order to obtain uniqueness. And under those conditions, he proved uniqueness. He thought more carefully about the analytic continuation. So I had some conversations with him and with his advisor, Helmut, and the problem is now completely solved.
That's fantastic. Fantastic. But I have to mention, your proof is from 1993. At least I think that's the year of publication. That was a long, long time ago.
Yes, it was a long, long time ago. Um, I, I still have fond feelings for it because I think this is, of course, a very important field, and yet theoretically, as far as I know, almost nothing is known. Um, and so this is I mean, this one theorem is, I think, perhaps a significant percentage of the almost nothing.
And this is one very important topic because I'm going to now switch to another theme, which is not developing a mathematics for AI, which, as you mentioned, is something which is, we're still learning how to do that. But how about using AI to do mathematics? So somehow back to computer-assisted proofs, but of a different kind. What's your view of that?
Well, so this is a very, very exciting idea. Um, uh, I have not I have not been even a consumer, but I've been a fan. I have been talking to Javi Gomez Serrano, who is part of I mean part a leading part of a team that that has produced solutions to problems in fluid mechanics, um, uh, which I think probably could never have been found otherwise. The point is that so the standard uh, the standard idea of finding, let's say, of finding a singularity developing from some PDE, from some fluid equation, is that you run a simulation and you look at what happens. And with luck, what happens is that a singularity develops, and the structure of that singularity is simple enough that you can guess the underlying mathematics, and then you know what it is that you should try to prove. For that matter, you can then produce a computer-assisted proof by producing an approximate solution, and then by using some contraction mapping theorem or something, prove enough estimates to show that near the approximate solution there is in fact an exact solution with the right kind of structure. So that was the most successful method in the past, and that's swell as long as the singularity you're looking for is stable. But of course, if the singularity you're looking for exists but is unstable, you can run all the simulations you want. You will never see it because it is unstable. However, if you let AI look for solutions, then it doesn't care whether the solutions are stable and unstable, and this has already been successful in a number uh, of important equations. Um, and so I think that this has a very great future. Now, um, uh, moving, all right, so moving um, from theorems in which I was the consumer to theorems in which I am a cheering fan, moving on from that to wild speculation, one can wonder whether AI will eventually actually prove theorems. Um, well, of course, AI has discovered patterns, and then one can take advantage of that and try to prove whatever the AI has discovered, and that has had in I mean that has already had some success. It would be very tempting to speculate on AI actually producing serious theorems in very important subjects and producing non-trivial proofs. So far, so far, AI doesn't reason very well. Of course, they are working on it. I am by far not an expert in that. It doesn't look close, but I think eventually it will happen. And then perhaps we can all become consumers of mathematics without all the hard work needed to produce it. We can let the computer do it.
Sometimes I think that we will see a proof of the Riemann hypothesis done by a computer. Okay, and not by calculating, perhaps by actually reasoning, and there's already some examples of very rudimentary thinking of that. Given at the speed at which these things, we already mentioned that maybe that will happen because we identify patterns and this and that. Imagine a situation where computers can prove Riemann hypothesis. You just say, this is my conjecture, and say, well, true, false. Okay, this is your oracle that you like to sometimes refer to when you do math, right? Your oracle is there in front of you. How powerful will we be when we have that? Or do you think that there will be some side effects to that power?
Well, I mean, everything I'm going to say is completely obvious. In such a case, the nature of the enterprise will change completely. Maybe mathematics will become even more of an art than it is now, and the taste of the people who decide which problems to enter into the machine will be crucial. In the past, mathematics has provided very important contributions outside of itself, contributions to science, contributions to many aspects of human endeavor. And I wonder what will happen if and when the power that you describe is given to mathematicians.
Progress will be incredible if we were able to do that, because then mathematics becomes as fundamental as it is now, but so much faster, right? And then, as you say, it's the driver. Right now, we still need the driver, right? We need. My question was, if someone has to pose the question, right?
Right.
The trick is in posing the right question.
Of course. Yes. So, my younger daughter is a composer, and we have had conversations comparing mathematics and music. And the difference between a mathematician proving theorems and a composer writing music rests on on very few points. One of these is that mathematics can be wrong, whereas it's hard to imagine music that is wrong. But maybe in the world that you describe, the difference between mathematics and music will narrow more.
There is this Fefferman Singularity Lab at ICMAT in Madrid, which is directed by Diego Cordoba.
Of course.
Right. And we're expanding that into Shanghai now.
Okay. Oh, delighted.
So, give us a homework problem.
Well, all right. Solve the Clay problem on the Navier-Stokes equation. How's that?
All right. Good. I'll write it down.
Okay.